This is an example of the first order transient game in Circuit Tutor for level 1, problem type 2, which is an RC type of circuit. So again, there is the introductory tutorial available, which you certainly would be a good idea to look at. I'm going to skip that for right now, and we'll select an easy problem here. There are, of course, examples at each level of difficulty, and it's also a good idea to look at some of those examples before you start. Okay, so this is a problem that has sources, resistors, and one capacitor, making it a first order problem. And as always in these transient problems, we have to analyze the circuit at a series of specific times. First at 0 minus, at 0 plus, right after the switch is, in this case, opened, because this is a switch that, as you can see, is opening at t equal to 0. Then we also need to find the Thevenin equivalent resistance as viewed from the terminals of the capacitor for t greater than 0, because that determines the time constant that is involved in this first order transient. And finally, we need to analyze the circuit at t equals infinity, in other words, after the switch has been open for a very, very long time, so that the transient has died out. And that helps us find the particular solution to the problem, which would be basically the in this case, the sought variable at t equal to infinity, which in this case is the capacitor voltage. So we need to do these things basically in chronological order from left to right here. There is, of course, help available at any time, and it's also always an option to give up if you get stuck at some point during the problem. And there's no penalty for doing that. You would simply see this full solution and then be given another problem of the same type to solve. Okay, so let's begin at 0 minus. That's just one instant before the switch is being opened here, and it gives us instructions. Basically, the first thing is always going to be to reconfigure the circuit at this t equals 0 minus, then to come out of the circuit editor and then perhaps simplify it and then solve the circuit at that instant in time. So our first step always is to reconfigure the circuit. So we just click on that button. So this is basically a new mode of the circuit editor, and in this mode you can only really do two things. One is to change the switch to something more specific, and then to change the reactive element to something else that will help you actually solve the circuit. We cannot do simplification in this mode. We have to go back into the circuit editor in the simplification mode in order to do that. So we don't want to try to combine things in series and parallel or anything of that nature. So because we're analyzing at t equals 0 minus, that's before the switch opened, so therefore that switch is going to be closed, or it's going to be equivalent to a short circuit. So I could either right click and change it to a short, or I could just click on the short button on the interface, which I'll do now. So that takes care of the switch. And then the second thing is the reactive element. So I'm going to select the capacitor here, and basically we know that in steady state the governing formula for a capacitor is I equals C dV dt. So because that switch has been closed for a long time before it's going to be opened, that means at 0 minus, one instant before the switch actuates, we will be in steady state. Any transients that did exist will have had lots of time to die out. In other words, many time constants. Therefore, we can assume that the circuit is in steady state, and since I equals C dV dt, ddt of anything will be 0, because the derivative, of course, of a constant is 0. So dV dt will be 0, which means I is 0. And if we have no current through a circuit element, remember that's equivalent to it being either a zero-valued current source or equivalently, more simply, just an open circuit. And we want to change it to these terminals so we can preserve that sought variable that we need to find. So I'm just going to click on this terminal key here, and that basically just changes that, and that's all we need to do in the reconfiguration mode. If you do need help with that mode, there is a help button here which will show you basically instructions on what to do in the reconfiguration mode if you forget anything about that. Okay, so we're done there. We just click done. And now we need to examine the circuit to see if we could simplify it, and clearly there's some things that we could perhaps do here usefully. So let's go into the circuit editor to simplify it before we do the analysis. That will make it easier. Now we could just do a full-fledged nodal or mesh analysis on the circuit, but it's always easier to simplify it if you can do that to make the analysis simpler rather than doing more work that you don't need to do. So here we clearly have two resistors in series. So the 7 ohm plus the 4 ohm will give me 11 ohm. So I'm going to change that to 11 ohms. And then the other resistor needs to become a short circuit because all the resistance is being included here now. Of course, we wouldn't make it open, and that would say that the initial resistance was infinite, which is not the case at all. So we'll check that combination, and that's correct. And now we might notice that we now have two resistors in parallel, namely the 11 ohm and the 4 ohm. The 2 ohm is not in parallel with those because it's connected to one of those two nodes, which is this one on the right, but it's connected to its own node down here that doesn't go anywhere, basically. It's not connected to this other node. So this one is not in parallel with these two. So we can only combine the 11 and the 4 ohm. So basically that would be the product over the sum for those two resistors. So that would be 44 divided by 15. So just doing that on my calculator real quick, that will turn out to be 2.933 ohms. And then this one has to change to an open circuit. So I just push the delete key, or I could come over and do it there if I want. That's gone, and now I just check that combination to see if that was correct, and indeed it was. Okay, so now is there anything further I can do? Well, there probably is something. I could do a source transformation here if I wanted. I am allowed to do source transformations in this particular mode, and you know, it's not really necessary here, but I guess we could do that. So let's just change that to a voltage source. So I'm going to click on a voltage source, and then I multiply the value that was 8 amps times this, since the open circuit voltage now is going to be, of course, the current times the resistance using Ohm's law. So the 8 amps times the 2.933, that's going to give me 23.46 volts. And now that resistor needs to be in series with the voltage source, not in parallel, to complete the source transformation. And so I can check that, and that is correct. And I suppose I could combine those resistors in series, but to be honest, neither one of them carries any current, so there's really no particular value in doing that. So I'm just going to skip that step and just say that I'm done. Okay, so now we can look at analyzing the circuit, and this is we do have more than one pair of nodes. I guess I could have maybe simplified to get rid of that, but it's also, well, we can call it a single loop, but there's not really any loop here actually. But for analysis purposes, it'll allow you to consider that a single loop. And basically, I just need this voltage. So I'm going to write a sought branch voltage equation, and that'll be for the VC of 0 minus. And really, I can see by inspection that because no current flows through this steady state capacitor, there's not going to be any voltage drop across either one of these resistors, and so really just this voltage is going to appear directly across the output. Now I do have to worry about polarity, because here the plus side goes to the plus side there, the minus goes to the minus side, so that has the same polarity. So it's going to be a plus side. Remember, that could have been reversed. If either one of these was reversed in polarity, then I'd have to have a minus sign. But in this case, it's a plus. So it's 23.46 volts, and I'll just check that. That is correct, and basically that's the final answer, so that's all I need to do at that instant in time. Okay, so the next step in the analysis will be to analyze at 0 plus. I can't go backwards in time, I have to go forwards, so I'm going to always go from earlier times to later times. So to analyze at 0 plus, and if I tried to analyze actually here, I wouldn't know what to do without having done the first step. So you really need to make sure you're always going forward in time and not trying to go backwards. Okay, so here you say, well, how am I going to find the sought value of this capacitor voltage at 0 plus? Well, the thing I have to remember about capacitors is they don't like to change their voltage suddenly. That's why they're oftentimes used in filters. And remember, the formula is I equals C dV dt. And if we were to change that voltage suddenly, the dV dt would basically become infinite, which means you'd have to have an infinite current. And you can't have infinite current through anything. So that really means that voltage cannot change suddenly. And 0 minus to 0 plus, well, that's just one instant basically. So the voltage at 0 plus is just going to be the same as it was at 0 minus. So all I have to do really is just enter that value. Whatever it was, I just enter it again. So that's 23.46. It's still defined, of course, with the same polarity, so there's nothing tricky there. And that's all I had to do, so that was very easy. Now let's do at t equals infinity and analyze at that time. So I just click that button. And now it's just basically changed the labeling here and made this VC of infinity for me, just for convenience. And now it just tells me what to do, which always starts with reconfiguring the circuit and then using the circuit editor if necessary, and then solving the circuit. So we're going to reconfigure, clicking that button. And now I'm back in the reconfiguration mode, but now I'm analyzing at t equals to infinity. And again, it reminds me not to simplify in this mode, so I can't combine things in series and parallel, for example. The only thing I'm allowed to do is to change the switch to something else. And now, because t is obviously greater than 0, you see the switch will have opened, and therefore this is now an open circuit. So I'm just going to delete it, basically, and leaving some things dangling there. But I cannot delete those just yet because I'm not in the right mode of the circuit editor to do that. It's just how the program works. Okay, and then I also want to change the capacitor. And again, since I'm going to be in steady state, remember that I equals c dv dt. See, at t equals infinity, any transient will have had lots of time to die out. And as long as it's a stable circuit, and frankly, any circuit that doesn't have a dependent source, it has to be stable. So then we don't really need to worry about that. And therefore, we will be in steady state. And since I equals c dv dt, the dv dt clearly has to be 0, which means the current has to be 0. So once again, just like at 0 minus, this is going to be an open circuit. And so rather than deleting it, which wouldn't get rid of our SOT variable, I'm going to change it to terminal so that we can still have that SOT variable shown there. So it'll give me an error if I try to delete it entirely, because that would get rid of the SOT variable. Okay, so basically I'm done reconfiguring. That's all I have to do. And now I might like to simplify this just to make it easier to do the analysis. So one of the first things I notice here is that, going back into the simplification and source transformation mode, is that these two resistors, as you can see, are just kind of dangling off into space. They don't go anywhere, and there's no path for current to basically exist in those resistors. Charge can't flow through there because it has nowhere to go. So we can just get rid of those. They're not really contributing to the rest of the circuit in any way. So we'll just delete both of those, and it tells me that was the correct thing to do. And you know, I could perhaps do a source transformation here. Again, don't really need to, but I can. So I guess I'll just do that. So I'll change that into a voltage source, and now multiply the 8 times the 4 is going to be 32. And I want this polarity, of course, the plus side needs to be on the head of the arrow. That's going to keep a consistent polarity with what we had before. And then now that resistor needs to move over in series with the voltage source. So I'll put it over there. I could have equally well put it over here. It doesn't really matter. And then I check my source transformation, and that's correct. And if I want to, I could combine those two resistors, but once again, that doesn't really matter since no current can flow here anyway. So I may as well just quit there. Okay, so now I'm ready to analyze the circuit. And again, this doesn't really have any loops, but the circuit, or I guess the program will allow me to call it a single loop. And now I just need to solve for that capacitor voltage again. So that's VC infinity is equal to, and there's no current here to multiply, right? Because no current can flow through an open circuit. Therefore, I'll just put a voltage value. And since there is no current in this 4 ohm resistor, no charge can flow through it, or for that matter, through the 2 ohm resistor. Therefore, neither one can have a voltage drop. So this voltage drop appears entirely across the capacitor. And it also has the same polarity. Notice plus goes to plus and minus goes to minus. So that's simply going to be 32 volts. So now I click check on that. That is correct. And basically I'm done. So I just say no more equations. And that will update my summary here to show me that I found the value at infinity as well as 0 minus and 0 plus. So the last thing I need to do, the only thing that I haven't done yet, is to find the Thevenin equivalent resistance seen from the terminals of the capacitor. So I'll click that button. And once again, it gives me instructions on what to do, which always starts with reconfiguring the circuit and then going into the circuit editor perhaps, or maybe I can just see the answer. So let's reconfigure. And again, I cannot simplify in this mode. I am allowed to kill independent sources because remember you have to do that when you're finding an R Thevenin viewed from terminals. So we might actually want to do that. So let's first of all start out by taking care of the switch. So the switch now, because again it's t greater than 0, that switch is going to be open. So I'll delete the switch. But again, I'm not allowed to delete these just yet because I have to go into the circuit editor to do that if I want to in the other mode. And let's see, so now I want to basically view the R-Thevenin from the terminals of that capacitor. So I'm going to replace them by a set of terminals. Now, before I do that, I want to take careful note that there are no dependent sources in the circuit. If there were, I wouldn't be able to put terminals there. In fact, it'll give me an error if I try to do that, because I would then need to have a test source, like a test voltage source with a SOT current, or a test current source, maybe a 1 amp current source, say with a SOT voltage, just like you would hook basically a multimeter to some terminals to measure the resistance. And that's basically what you're doing on paper, is sort of using a virtual multimeter. But in this case, I don't need to do that because there are no dependent sources. Therefore, I can just use resistive simplification. So in that case, I'm just going to change it to a set of terminals, and it automatically puts that little R-Thevenin thing on there for me, indicating that I'm viewing that R-Thevenin. Now, I am allowed to kill sources in this mode just to save time. So I may as well go ahead and do that. My current source, remember, if you want to kill a current source, it doesn't go to a short circuit because it needs to have zero current. And the circuit element that has zero current is a zero valued current source, i.e. an open circuit. So I'm going to delete that to represent an open circuit. And that completes all I can do in the reconfiguration mode. Okay. So now I have a couple of options here. One is to go into the circuit simplification mode, and then I would delete these dangling resistors that have no role, and then I could combine the 4 and the 2 ohm. But really I can just kind of see that by inspection here. So I think I'm just going to short circuit all that, no pun intended, and just go and put the final value in here, which is clearly going to be 4 ohms plus 2 ohms. So I'm just going to put a 6 in here, and it will accept that. Okay, so now basically I've determined everything I need to do the transient expression. So it's put me automatically into the mode where I'm going to input the final transient expression. And I just have to pick the appropriate equation type. So this is going to be a transient voltage, VC of t. So I have to select that type of term. And it basically gives me the proper format. That's something that you want to kind of know, because on a test, of course, you're not going to be given that, so you would want to probably know that expression. But here it is providing it for you. So there's really no choice there. I just get one of those. And first of all, we have to fill in the blanks. Well, that's all we have to do. So we'll notice, first of all, that at t equals to infinity, we'd have e to the negative infinity over something, which would be 0. So this term is going to go away no matter what this coefficient is at infinity, and we're going to be left with this. So this has to be VC of infinity. So VC of infinity I've calculated as being 32 volts. So that tells me that this value has to be simply 32 volts. Secondly, when t is equal to 0, one of the other extreme cases, or 0 plus to be precise, then the exponential is just going to be 1, because of course e to the 0 is 1. So that means that 32 plus this number must equal the VC of 0 plus, which is 23.46. So now I will need my calculator, and basically I'm going to take 32 minus that, 23.46. Oops, try that again, 23.46. And that's 8.54. And again, I want to subtract that, so it's going to be minus 8.54 volts there. And again, this minus this at t equals 0 will give us this 0 plus value, so that should be correct. And finally, I need to enter the time constant, the value of tau here, in the denominator of the exponent. And for an RC circuit, remember that's R-Thevenin times C, which you have to know. And the R-Thevenin, we know, is 6 ohms. The C is 5 farads, so that's going to be 30 seconds, a rather long time constant for this circuit. So now I'm ready to check, and that is correct. And basically, I just say no more equations now because I'm done. And I do have the option to get a more detailed explanation in case I was unsure about any of the process there. And so we'll just have to wait for a moment while it Right, it's a whole lot of stuff on the screen here. And so it's showing here basically the general procedure that you follow, and then it's going to show the steps that you do at each point in time. So there, 0 plus, it basically shows you how do that analysis with the capacitor changed to an open circuit and the switch being closed. Shows simplifying the resistors, and basically then just in this case it did a mesh analysis or single loop analysis, which is similar to what we did. We did a source transformation, which is another way of doing it. So there's more than one way to usually do it, and this will show you maybe alternatives. So it might be sometimes worthwhile looking at this. You might get some hints as to how to do problems more easily in some cases than what you may have done. But in any case, it might be useful to look at this. And then it shows basically finding our Thevenin, which was the 6 ohms, and then the final expression. So that completes this example of the first order transients circuit. Thank you.